Hi, I'm Stephen Neshaba, and I'm here to help you out with a kind of a problem in kinetics, which has to do with getting initial rates and a rate constant from what we call time concentration data. So the situation is this: we've got a reaction NO3. It's an atmospheric oxidant, reacts to form products, and it turns out it's known that the self-decay of that process is a second-order process. And so let's suppose somebody has done these measurements in minutes, time 0, 10 minutes, all the way down to 500 minutes. And these are the concentrations that were measured for NO3. It's in micromolar, that's 10 to the minus 6 molar concentration units. Now you can kind of see from this that 1.47 all the way down to 1.19, the concentration has not gone down very much in that time period. And you know, if we were to display the concentration of NO3 graphically, we'd see that, you know, we're only, you know, this far into the process, okay? And so we don't have the possibility, we don't have the data available to take something like a half-life to convert it into a rate constant. What we're going to have to do is just the initial behavior right there to deduce that. So how are we going to do that? Well, the initial rate is just the negative of the slope of the nitrogen NO3 concentration over time. That's the rate rule. So we would be talking about this slope right here. There's a change in the concentration of NO3, and we would divide that by the change in time. That would be delta t, okay, for some interval. Now, it's most convenient to use the first two numbers here, so that would be actually from 0 to 10. Okay, so that's how I'm going to set this up. I've said the rate is equal to a minus change in nitrate divided by the change in time. That's why I have 10 minus 0 at the bottom here. That's that line minus that. And in the numerator, I have the two concentrations there, that number minus that number. And if you carry out that calculation, then what you get is 7 times 10 to the minus 7. And the units have to be micromolar per minute, which I'm going to write micromolar minute to the minus 1. Okay, so that's the rate. And you can see that it's a positive number because the numerator here was a negative number, and that cancels out that negative there. Okay, so we got the rate from the initial time concentration data. How do we get the rate constant? Well, we're told that this is a second-order kinetic process, and so we can say the rate is equal to k times some concentration, the concentration of NO3, but since it's second order, I have a problem here, right? I need to have written squared right there. That's the rate law for a second order process. And well, what do we know? I know the rate at that start of the reaction, so I know that's 7 times 10 to the minus 7. Do I know the concentration at that time? Well, yeah, I can just pick up that concentration right there. And of course I need to square it. And if you do all that, then you get 0.32. And if you think about the units, it's micromolar to the minus 1, minute to the minus 1, and that's in order that all the units work out properly. So there we've done it. We've got the rate constant and the rate all from the first two data points in this tabular data. Okay.